Hello and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques course. In this module, we will wrap up the discussion of LP modes by talking about power confinement as a function of the normalized frequency, and then talk about the physical characteristics of these fibers which are important for communication purposes. Okay. We have already seen that LP modes are not really the true modes, but they are simplified modes, okay. And these simplified modes are quite popular in the literature because delta, which measures the refractive index difference between the core and the cladding, is so small that we can consider it to be equal to 0. But there is another important thing that we need to understand is that these different modes that are propagating or that can be technically excited by appropriate conditions, these modes actually have different amount of powers concentrated in the core and the cladding, and that all has to do with the kind of the electric and magnetic field structure that you are going to obtain for these modes. Okay. We will not do a full calculation, but I will tell you the important thing that you are looking for in addition to the mode structure itself or the propagation constant itself is what is the. So, if you launch a certain total power, what is the amount of the power that is actually propagated in the cladding, or it is actually in the cladding, not in the core. Okay. So, the total power, if you assume, is split between the core and the cladding, okay, assuming no losses or other things that we are going to talk about later on. If you now just take the total power and split into core and the cladding, you want almost the power in the cladding to be equal to 0, because you do not want any power loss, okay, on top of whatever the absorption losses that the fiber material itself will present to you. You do not want most of the power to be lost in the cladding, you want the power to be in the core. Okay. However, for different modes, depending on where the operating value of V number or the operating or the corresponding propagation constant beta is, there will be different power confinement. Okay. When you operate, for example, the fundamental mode LP01 mode or the HE11 mode, both are essentially same, very near to the cutoff frequency. Remember, their cutoff frequency is just at V equal to 0, right. At that point, what you will actually see is that this would be the power. So, if on the y axis I plot power in cladding to the power total, then this would be almost equal to 1 for quite a bit of values of V very nearly equal to 0. What it means is that at cutoff, LP01 mode has most of its power not confined in the core, but it is propagating in the cladding, which is completely waste for us, because the power in the cladding will not be able to sustain long distances, and you are simply wasting the power by sending more of that power into the cladding. Okay. You want more power if you want to cover more distances, but that is not an ideal situation, because cladding has extremely large decay constant. So, the power is not really confined, the field actually spreads out, most of the field actually lies in the cladding. So, if for example, this is how a core would look like, okay, so this is a core and this is the cladding, then at cutoff or near cutoff, most of the power is actually concentrated in the cladding, very less of the power is actually concentrated in the core. In fact, at V equal to 0, this ratio of cladding power to total power becomes equal to 1, which means all the power that we have launched is essentially sitting in this cladding. But when you start moving away from V equal to 0, you will actually start seeing that the power confinement or the power in the cladding starts to go to 0. Let us look at the special 2.4 case. Okay. So, at 2.4, the corresponding power confinement that you will actually see is just about 0.3. In other words, there is about 70% of the power in the core and 30% of the power is actually lost in the cladding. Now, that is actually not very small, okay. But the trade off is that if you operate it below or very near to V equal to 2.4, then this is the only mode that is propagating, and because this is the only mode that is propagating, the associated dispersion because of multi-mode propagation will not occur. So, you are trading off how much power can be confined in the core. Yes, if you operate at larger values of V, most of the power will be confined in the core itself for the LP01 mode, but operating at a larger value of V also means that you are potentially exciting many other modes, higher order modes, and that is not a very good idea, because those higher order modes will actually start eating away the power and they are going to contribute to intermodal dispersion. Okay. So, at 2.4, which is very close to the cutoff value, there is just about 30% of the power in the cladding. Any attempt to reduce this one would only mean that you are exciting more modes, because you would have to go to larger values of V. A same situation will occur for the next mode, which is LP11 mode. Remember, its cutoff is around at 4, and at that value the corresponding power or the confinement factor is almost close to the case for the LP01 mode itself. So, it will also start at around 1 and then come down like this. Okay. It would come down much faster here. So, I should better show that one. Starts at 1, but then it comes down rapidly for larger values of V. Okay. So, you can see that other modes also have this kind of a behavior. Okay. So, wherever you are trying to confine the modes in a step index fiber with LP01 modes, if you are trying to confine power into the core, then you need to operate at a reduced value of V corresponding to the cutoff. Okay. Of course, you need to get the cutoff, and from the cutoff you need to operate it around the cutoff or maybe slightly above the cutoff. But if you start operating far away from the cutoff for the lower order mode, there is a good chance that higher order modes also start propagating. So, it is a trade off that you have to determine how many modes can I support in this communication system versus what is the power confinement that I want in the core. Okay. Depending on different applications, this is for the communication application. However, if your idea is to treat these different modes or this fiber just to collect light, you do not mind operating it at a larger value of V, because there you are not really looking at dispersion or anything, there is no information being transferred, but fiber is simply being used as a connecting tube. Okay. So, your goal would be to collect as much of power is possible. So, you want most of the power to be confined in the core, and you can achieve this by operating at larger values of V. This situation is quite common in biomedical applications of fiber optics, where this optical endoscope kind of a thing, you have this fiber. So, fiber end will have excited many modes. Exciting many modes also homogenizes the light that you are going to get. It will not give you those individual mode structure, but you will actually get a uniform illumination and a uniform collection pattern. And by design, the value of V is quite large for this, or the operating wavelengths are quite in such a way that the corresponding value of V is so large that you are not really dealing with single mode, but you are dealing with hundreds of modes. And that is good, because as I have not shown you the other pictures here, you can refer to Glock's picture or Glock's paper for these pictures, but operating at larger values of V means that most of the power is actually confined in the core and very less power is confined in the cladding. Okay. So, this kind of completes our understanding of LP modes. Now, whenever next time I talk about a mode, what I am actually talking about is this one. So, this f of x comma y, alternatively this could be f of r comma phi, would describe the LP modes. Okay. It would describe the LP LM modes, but please remember these mode structures are in the transverse direction, because along z they would all be propagating as e power minus j beta Lm z, where beta Lm is the propagation constant for the LP LM mode, and this f of x y or f of r phi is the transverse mode distribution. Okay. Which is what we have studied so far. Okay. These are not longitudinal modes, these are the transverse modes. Okay. It is in this fashion, the corresponding electric and magnetic fields, that light actually propagates through the optical fiber. Okay. So, this is all about LP modes and the modes. Now, let us look at some physical characteristics which are necessary for communication purposes and of course, for many other purposes as well. One of the simplest things that you would want to know when you are going to use an optical fiber is that if this is my optical fiber, okay, of certain length, let us say whatever the length that is there, if I launch a certain amount of power which I will call as P in, I have not discussed how to launch powers into a mode. So, we will have that discussion later on when we start looking at mode converters or mode launching, but for now just take it on faith that it is possible for me to actually connect a light source, which usually happens to be that a laser, or in some cases it would be an LED, light emitting diodes. Whatever the power that is given off by these lasers and LEDs can be launched into the optical fiber. Your question most likely would be, what is the output power? Why is this important? Suppose you are communicating by a simple digital modulation process. Okay, a simple digital modulation would correspond to sending a bit 0 by sending no light pulse, but for bit 1 you are sending a light pulse of certain power, which I will call as P in. So, you are sending this sequence of optical pulses at a certain bit rate, okay, and these pulses are now propagating inside the optical fiber. At the receiver you have a detector, okay, this is my notation for a detector, okay, which I will also sometimes simply write it as PD. PD stands for photo detector. We are going to discuss these components later on, but for now the photo detector will simply look at the optical power that is falling onto this, which we have called as P out, and produce a current which will be proportional to this P out, where R is called as the responsivity of the diode. It measures how good the response of the photodetector to the incoming optical power. Okay. So, you send in say 1 milliwatt and let us say you get 1 milliamperes of current, then the responsivity of this device would be 1 ampere per watt. Okay. Of course, it does not mean that you can just take 1 watt of optical power and expect 1 ampere of current. Maybe the photodetector itself would break down when you start putting in lots of power. So, it is not a linear relationship, but the units are always measured in terms of ampere per watt. In most communication photodiode receivers, the unit is milliampere to milliwatt, okay, indicating that you are working in the milliwatt region of optical power, and the currents that you generate are in about milliampere range. Okay. So, you need to know this information P out, because what you actually receive will not be the full power P in, but what you would receive, assuming no other distortions, would be this power, okay, which I am showing in green color, right. This green color is the output power P out that you will actually get at the output of the optical fiber, and depending on, you have to put a threshold here to detect whether your received bit or received pulse is greater than this threshold or less than this threshold. So, if the power is greater than the threshold, then you declare the received bit to be 1. If the power is less than the threshold, you declare it to be the bit 0. Okay. In order to make this decision, you need to actually look at how much would be the minimum optical power required, okay, or minimum optical power that my photodetector can detect. Okay. If I send in optical power at say 20 picowatts, my photodetector may not respond. Okay. It says that no, you please give me a certain optical power, let us say 1 nanowatts of power, nanowatts of optical power, so that I can convert that 1 nanowatt into a current of 1 nanoampere, and that is the minimum optical power that I require. If you send in any power which is less than that minimum optical power, which is also called as the sensitivity of the receiver, then the receiver will not be sensitive. It will not be able to distinguish whether you have transmitted an optical power or you have not transmitted an optical power. And who sets that limit? How does the optical fiber change the power? Because there is going to be absorption, right. The optical fiber, if you remember the structure that I showed you in the first module, is actually something like this. It has a core, it has a cladding, then there are jackets, and all this is not some kind of a hollow tube, they are actually solid materials. Okay. They are made out of fused silica, and you know that no material will be completely loss free. In optical fiber cases or in optical fiber situation, these are the following typical losses. So, you have losses because of electronic transitions, I will describe this in a moment. You have losses because of vibrational transitions or vibrations of the molecule. So, molecular vibrational transitions. Okay. Then you have loss because of impurities during the manufacturing process of the fiber, and then you have some other losses. Main loss is the Rayleigh scattering loss. Okay. These are typically the loss mechanisms that you will see in an optical fiber. Electronic transition means that if you actually look at the material that we use for optical fiber, that is a fused silica material, okay, and the fused silica is a semiconducting material. It has a certain valence band and a conduction band. The band gap is around 9 electron volt, which means that only when light wavelength is about less than 100 nanometer, then this would have sufficient energy for any electrons or for any holes here to jump up to this one. Okay. So, I mean you can actually have this electronic transition only when you have given sufficient energy to dislodge a hole from the valence band and kind of connect it to the conduction band, or basically to transition the elements in the valence band and make it into conduction band. It is not the holes, it is actually the electrons which move up and transition. Okay. But for this to happen, you need extremely high intensity optical power or high optical I mean you need a frequency which is very low, you need energy to be very high. Okay. So, that energy, a high energy can be obtained in the X-ray regime or in the ultraviolet regime, because as you go to the infrared regime, the value of lambda starts increasing, and since energy is inversely proportional to lambda, okay, at infrared wavelengths, which is say near infrared wavelengths, which is around 1 micrometer, the electronic transitions are rarely going to happen. It is not that they will not happen. Quantum mechanics tells you that there is a finite probability for electrons to jump from valence band to the electron band by absorbing the energy that is propagating through them in the form of optical photons, okay, photons being the carriers of light. It is possible that there is a non-zero probability that they will jump, but most of the times they will not jump. Okay. So, this electronic transition induced losses are mostly in the ultraviolet regime, not really in the infrared regime. Okay. And there are very few applications, or at least those applications which I am aware of, where light is less than 100 nanometer, but it is there, and we do not normally communicate at this wavelength. So, we do not really worry about electronic transitions. What about vibrational transitions? Vibrational transitions mean that these are the silicon and oxygen molecules, and this is an SiO2 molecule, right. So, there is one silicon and then there is two oxygen molecules. So, I should actually write down better. So, let us say this is silicon, this is oxygen, this is oxygen. Then you can have vibrations in this way, up and down vibrations, or you can have vibrations in this linear way, that is it would be moving in this way, right, or it could actually the entire system could move from left to right. Okay. So, these vibrations are the different modes, or these are the different modes of what are called as acoustic waves or acoustic phonons, and when light propagates through the fiber, then these different vibrational transitions can actually occur. Okay. And these acoustic optics, because they have to keep moving here and there, or they have to vibrate, they get their vibrational energy from the optical photon. So, they actually absorb certain optical energy and then convert that optical energy that has been absorbed into these vibrational transitions. Okay. In fact, these vibrational transitions are so important, because when you send in additional light waves at different frequencies, you will actually be able to observe what is called as scattering effects. Stimulated Raman scattering and stimulated Brillouin scattering are some of the results of these vibrational transitions, which of course take away most of your energy that is propagating in the fiber. Okay. However, these set of loss mechanisms are not really, of course the vibrational transitions actually start becoming prominent at after about 1.5 nanometers. So, these are fairly okay in the infrared regime or in the near infrared regime. So, after 1.5 micrometer, the loss mechanism because of vibrational transition starts to increase. Okay. However, by far, or at least before 1970, the idea of optical fibers was proposed in 1966 or 1960s. People knew about that, but for communication purposes it was proposed by a person called Charles Cow, with whom we about whom we talked about in the first module. And what Charles Cow said was that it is not the problem of the material itself, it is the problem in the current manufacturing processes. Okay. And these current manufacturing processes had one major contamination or impurity to the fused silica, and that contamination was the water ions. Okay. These are the OH hydroxyl ions, and these ions or these water molecules would actually absorb most of the light, resulting in losses which exceed about 1000 dB per kilometer. So, you would actually get no photons at the output, and the entire optical fiber communication would seem to have not happened. However, in 1969 three researchers from Corning Glass Works actually reported, Keck, Maurer and Capron, they reported a fiber whose losses were less than 20 dB per kilometer, because they came up with a novel manufacturing method. They called, we will talk about the manufacturing sometime later, but they came up with this novel manufacturing method for optical fibers which could remove all these water absorption or water impurities. So, you have to clean this fiber up many times so as to remove any sort of external impurities, except those impurities or dopants that you are going to introduce in a controlled manner in order to change the refractive index of the core and the cladding. All other impurities has to be kept minimum. Even 1 parts per billion of hydroxyl ions could actually lead to large amount of losses, which makes the optical fibers completely useless. So, impurities mainly from water ions was a major cause, and these water ions actually had nice characteristic peaks. So, it had these peaks, and now this is how the loss would look like as a function of lambda. So, this peak initially, or this valley initially, was around 800 nanometer, where the loss was thought to be minimum. So, most communication, optical communication happened here in this one. So, this is the first generation regime, and then there is another valley down here. I might not have sketched this valley down correctly, but there is a valley down here which is close to 1.3 micrometer, and then there is one final valley. I should probably write it like this. And this valley, where the losses are now just about 0.2 dB per kilometer, I will tell you what this is, happens at 1.5 micrometer. So, this is the first generation, this is the second generation, and all other generation optical fibers are now working at 1.5 micrometer light. So, what exactly is this 0.2 dB per kilometer that we talked about? Before that, let us just finally close down our losses. So, initially if you look at the losses at lambda, which is close to 0, right. So, this is the attenuation, which I will call as alpha. The units of this one, that is usually dB per kilometer. I will tell you a little bit about that. The losses, so there is some there is these losses called as Rayleigh losses or Rayleigh scattering losses, which actually decrease as lambda power 4. Whereas this increase that you would see is actually because of the vibrational transitions that we discussed about that. So, it decreases as 1 by lambda power 4, which means that Rayleigh scattering is very prominent in the ultraviolet regime and starts to decrease, but as the Rayleigh losses starts to decrease, the vibrational transition starts to increase at the tail end. So, where they two meet, that is where you actually have a minimum loss. It does not look that way with the figure that I have drawn, not very nice figure, but when these two meets, that is where you actually have a minimum loss. And that minimum loss happens to be at 1.5 micrometer, and these are the different loss mechanisms. But I have been talking about these losses in terms of some quantity called as dB per kilometer. What exactly is this dB per kilometer? As I told you, if I take an optical fiber of certain length L, send in a power P in and get the power P out, I expect that this power P out, which would of course keep varying with respect to L, as goes as e power minus alpha L times P in, where this alpha is what is called as natural units of attenuation. So, sometimes called as Nepper per meter, but because it is not really nice to work with Nepper per meter, we convert this one by multiplying certain quantities into a different quantity called as dB per kilometer, because expressing quantities in terms of dB is very useful to us. It allows calculations to be quite simple. So, if I were to calculate the output power, which is a function of L, as input power times 10 to the power minus alpha, measured now in terms of dB per kilometer times L. So, if you know what is the power that you got out and you know what is the power that you put in, then by taking log on both sides to the base of 10, you will be able to find out what is the power that 1 by L would actually be the loss that you are going to find out. And because P out is smaller than P in, this loss factor is positive. It does not mean that the loss is positive, what it simply means is that the units for alpha is positive, but the power would actually decay as 10 to the power minus alpha in dB per kilometer times L. So, I see that I do not have much of a time. So, what I will do now is to stop at this point. We do have a little bit more to say about dB scale when we talk about attenuation in the next module. We will wrap up the attenuation in the first few minutes in the next module, and then discuss the second physical feature which I have hinted to you as being very important, called as dispersion. Okay. Thank you very much.